This lesson is on 1.4 composition of mixtures of AP Chemistry. If you have followed my video on lesson 1.3, you're going to find 1.4 to be very, very similar in the math that we're doing. So that's great that we have some consistency. So hopefully that will make this lesson a bit easier for you. So first, a little bit of background on what some of these terms mean. I want to remind you that matter is categorized into two types. There are pure substances and there are mixtures. Okay, so two main categories. Within those two categories, right, that we see here, 1 and 2, there are subcategories. So the two different types of pure substance include elements and compounds. An element is a single element that you see on the periodic table. It's one of those. Nitrogen, carbon, for example, those would be considered elements. A compound is two or more different elements that are chemically bonded together. Carbon dioxide, which is written as CO2. So you see that those things are completely bonded together because they're written together. So when you see those, right, something like CO2 is going to be a compound, whereas an element is something like helium. Side note, a term that you'll hear us refer to often as a molecule. So what is the difference in a molecule, an element, and a compound, right? Well, an element, again, is one thing from the periodic table. A molecule is very similar to a compound, but molecules are two or more same or different elements chemically bonded. So the difference is N2 is a molecule, right, that you see here. Two nitrogens bonded together. That's going to be a molecule, but it's not a compound. Carbon dioxide is both a molecule and a compound because the term molecule doesn't differentiate whether they are the same element bonded together or different elements bonded together, whereas a compound does, right? And remember, sodium, for example, all by itself, that's just an element. So that's something to keep in mind throughout the entire year because you're going to hear me refer to those terms and they do mean something just a bit different. All right, so on to our second type of matter. First, we talked about pure substances. Now we're on mixtures. Mixtures, again, two categories, right? Lots of twos in this lesson. So mixtures are two or more different compounds or elements that are not chemically bonded. They're placed together, perhaps in a container, but they're not chemically bonded to one another. Okay? A homogeneous mixture, our first type, we're going to call those solutions throughout the year. That'll be the more appropriate term for AP Chemistry. They are defined as being uniform throughout. Oftentimes, this is something dissolved in another substance, salt water, sodium chloride, and water, right? Those things are considered to be dissolved, and that is considered to be a solution. Heterogeneous mixtures we'll often refer to as suspensions. Those are not uniform throughout. Oftentimes, they're layered or chunky, and we don't deal with these quite as much in AP Chemistry as we do solutions, but still important. An example of a heterogeneous mixture would be the first thing that comes to mind is like a salad dressing, a Italian salad dressing with all the little chunky pieces, right? You tend to see that will separate out. You shake it and they seem to kind of mix together, but they quickly separate back out into layers. So let's talk about the math. I mentioned already that this math is going to be really similar to our 1.3 math that we did with pure substances, right? So notice, right, we're dealing with the two types of matter. 1.3, right? 1.3 dealt with pure substances. 1.4 is going to do math with mixtures. Right? Super similar. All right, so our first example is we have that data was collected regarding a mixture of lithium chloride and beryllium chloride. We're given the mass of each of those two, and we're given a total mass of this mixture. And we're told to find the percent of lithium chloride by mass in the mixture. So I want to remind you, percentages are always a part over the whole multiplied by 100 to turn it into a percentage. So in this case, this is a very easy question that is disguised to look a little scary and intimidating. We have all the math we need. We don't need to reference the periodic table or do any conversions here to solve this problem. We simply want to put the mass of lithium chloride over the mass of the mixture. All right? And notice the question said by mass. That's something we want to watch out for. Right? What type of percentage are we looking for? So mass referring to grams. So we're going to take our 3.17 grams of lithium chloride, divide it by our total right? Mixture amount, which is 9.44 grams, multiplied by 100. Your calculator should give you 33.6% lithium chloride. Moving on to B of number 1. We are asked to find the percent by mass of lithium in this mixture. Okay? Same data we were referring to. We're still on example number 1. And this time we got to think a little bit, right? Because we want to know lithium. And we don't have lithium, right? When we look at that chart, we're given lithium chloride and we're given beryllium chloride. We're not given just lithium. So we're going to have to think a bit of how can we find lithium. Well, we want to use the data that we have that contains lithium. It would do us no good to use the data that contains beryllium. It's going to be a much less direct method. So what I'm going to do is I'm going to set up a ratio of our given number of lithium chloride from that table. I'm going to multiply it by the mass of lithium from the periodic table divided by the mass of lithium chloride, again from the periodic table. So I calculated the molar mass of lithium chloride. That's where this 42.39 came from. Right, that's 6.94 plus chloride's 35.45 grams per mole. Added that together to get 42.39. So when I do that, I have converted lithium chloride to lithium. So I end up with 0.519 grams of lithium. So now I have the mass of lithium, but not the percent. Percent is the part over the whole. So I'm now going to take our grams of lithium, I'm going to set that up here, divide it by the 9.44 grams of the total mixture part over the whole. Multiply that by 100 and I get 5.50% lithium. Now, before I go any further, I do want to reference that these are Michael Faribault problems that have been adapted from his lecture notes on Unit 1. Okay? The majority of the problems in this section are adapted from Michael Faribault, and I want to be sure to give credit where credit is due. You'll definitely find his YouTube channel linked in some of my videos. All right, moving on. Part C of number 1 tells us to find the percent by mass of chlorine in the mixture. Similar to part B, but this time we're looking for chlorine, and we've got to remember that we have chlorine in 2 different parts of this problem, not just in one. So if we'll go back to this chart, right, our total mass of our mixture consists of 2 parts, lithium chloride and beryllium chloride. Both of those contain chlorine. So we're going to have to deal with finding the chlorine in both parts of those in order, and get the sum of that in order to figure out the percentage of chlorine in the total mixture. So similar, but we're going to do 2 steps in this one, or 2 parts. So we're going to take our 3.17 grams of lithium chloride that was given, and we're going to multiply it by the mass of chlorine over the molar mass of lithium chloride. And we found the 42.39 in part B, so that saves us a little bit of extra work. But if not, just for reference, we got this number from the periodic table. Lithium is 6.94, and we added that to the chlorine, which is 35.45. Right, and the total of that's 42.39. And then on top, we're using the mass of chlorine. There's only 1 chlorine in a lithium chloride compound, so we put the 35.45 on top. That helps us to convert from grams of lithium chloride to grams of simply chlorine. When we do that calculation, multiply by 35.45 and then divide by the 42.39, our final answer should be 2.65 grams of chlorine. All right, we're going to repeat this process with the other given number that also contains chlorine. We've got 6.27 grams of beryllium chloride given in our table at the beginning of the problem. We're going to find the total mass of beryllium chloride, again from the periodic table. We get this from adding the mass of beryllium and the mass of 2 chlorines, because notice it's Cl2 here. When we do that, we get a total of 79.91. Now on top, our mass of chloride out of this mixture is a little different. Notice it's different than the 35.45 given in our previous step. Why? Notice these numbers are different. Well, BeCl2 has 2 chlorines in it, so we've got to account for 2 of those being part of this, the mass of this mixture. So this compound, 70.90 grams of chlorine is 35.45 multiplied by 2. So now we're ready to do that conversion. 6.27 in your calculator times 70.90, enter, divided by 79.91. You're going to get a value of 5.65 grams of chlorine. Add those 2 together, right? The sum of those gives us the total grams of chlorine in the mixture. So we arrive at a number of 8.21. So now to turn that into a percentage, part over the whole, so the 8.21 grams of chlorine divided by the 9.44 grams of mixture. Remember that number was given in the problem as the mass of the total mixture. And of course, multiply by 100 to get our percentage. We end up with 87.0% chlorine. Number 2. An example of a solid labeled as AgNO3 may be impure. A student analyzes the sample and finds it contains 68% silver by mass. Lab problems dealing with impurities are pretty common in AP, so this is something that I don't want you to find intimidating, some language I want you to become comfortable with. We're asked to calculate the percent of silver by mass in a pure sample of AgNO3. Okay, so all we have to do there is find out the molar mass of Ag, nitrogen, and oxygen, add that together to get the total mass of an AgNO3 molecule. So 107.87 plus 14.01 plus oxygen. There are 3 of those in the sample, right? O3, so 16 times 3 gives us 48. Sum of those 3 together is 169.88 grams per mole of AgNO3. So we're going to take those grams that we just calculated, okay, and we're going to find how much silver makes up of that, find that percentage part over the whole. So our value for silver was 107.87, right? Because remember, that's what we're asked for, the percentage of silver in AgNO3. So 107.87 divided by that total we just found. Again, multiply by 100 to get a percentage. We end with 63.5% silver. That's if it's pure. Let's compare that number to the number we were given in example 2, right? So when it was analyzed by a student, they found silver to be 68. 68 higher or lower than 63? Okay, that's something we need to consider when we're moving on to part B here. B says, which of these is most likely to represent the solid sample that was analyzed by the student? Does the mixture contain AgNO3 and AgCl? Or AgNO3 and AgBr? The difference in these two is chlorine and bromine. Now, those are the difference makers. So let's think about this for a minute. If we know that pure silver nitrate is 63.5% silver, figured that out. This mixture is 68, we just said that because the student analyzed it and found that, given in the problem, right? Given, we just found that with math, our calculations. We know that 68 is greater than 63. So again, is it going to be chlorine or bromine to cause that percentage to be greater? So let's justify this with math. And then you'll be able to figure out mentally how this should work with math without making this so tedious. So molar mass of AgCl and then molar mass of AgBr. Let's find that and let's compare them, right? So we find the mass to be 143.32 for silver chloride, for silver bromide, 187.77. Those numbers came from adding them together from the periodic table. Now, let's find a percentage in each of those. How much does silver make up of silver chloride? How much does silver make up of silver bromide? So part over the whole. Our silver part's 107.87 from the periodic table in both. Divide each one by the molar mass. Right? When we do that, don't forget to multiply by 100 so we get our percentage. 75% silver, 57% silver. Right? So comparing those numbers, which one is greater? The biggest thing we want to look at is which one is going to be greater than the pure percentage of silver in the mixture. And if we look back, right, we know that the pure percentage in the mixture was 63%. So it's supposed to be 63%. It's actually 68%. Which one of these two, right, 75 or 57, would cause it to be 68 rather than 63? In this case, probably the larger one, right? The larger percentage, the one with more silver, is going to increase the value. So it's more likely to be the 75% because it's bigger than 63. It's bigger than the pure value. So how would you term that appropriately for an answer? On a free response question, you would say, and I've got that in quotations here, it is more likely that this mixture contains AgCl because the percentage of silver by mass in AgCl is greater than the 63.5%, which is found in a pure sample. Example 3. The student needs to analyze a mixture that contains barium chloride and sodium chloride. The student dissolves a 6.75 gram sample of this mixture completely into water and adds an excess amount of sodium sulfate, aqueous, which means it's dissolved in water. A white precipitate of barium sulfate, solid, is formed. A precipitate refers to a solid that forms when we combine a couple of different solutions in a mixture equation, where we have barium chloride aqueous solution plus sodium sulfate aqueous, and we form 2 sodium chlorides and a barium sulfate solid. Notice the sodium chloride is aqueous, it is dissolved in water. It tells us the solid precipitate, that's the barium sulfate, right? Precipitate solid is filtered, dried, and weighed. And its mass was found to be 2.36 grams. I just want to label that for us. That is the barium sulfate solid precipitate, 2.36 grams. 2.36 grams. We're asked to calculate the number of moles of barium sulfate solid that's recovered in this experiment. So it has a lot of terms. There's a reaction and lots of words. It can be a little intimidating, but this one's not bad. So the first thing we want to do, since we are looking for barium sulfate and we want to find moles, we don't have moles, but we know something about grams. We're given grams of barium sulfate. So let's start with that because that is the thing we're looking for, barium sulfate. So we got our 2.36 grams. We're going to set up a ratio just like we did before, right? Through dimensional analysis. We're going to find the molar mass of barium sulfate because we need these grams of barium sulfate to cancel. So I need grams of barium sulfate to go here on the bottom. So I find barium on the periodic table, see that it's 137.33, sulfur 32.06, 16 times 4 oxygens gives me 64. I arrive at a total of 233.39 grams. That's where this number comes from in our math. Now that's how many grams are in 1 mole of barium sulfate. So on top I simply put 1 mole. This is math we've done many, many times previously in chemistry. So 2.36 times 1 gives us still 2.36, and then divided by 233.39 gives us an answer of 0.0101 moles of barium sulfate. Part B, we're asked to now find the percentage of barium chloride by mass in the mixture. So we want a percentage. So we're looking for a part over the whole as always, right, with a mixture. Here's the thing. They gave us no number for barium chloride. They only gave us a number for barium sulfate. So let's back up and look at that given reaction, right? We want to find this. We have no information on that. What we do have is this, right? We've got that. So how do we get from here all the way to there? So it's going to take us a little further on the math. So here's what we're going to do. We're going to take our moles of barium sulfate that we just found in part A, and we're going to change moles to grams. So we're going to start with 0.0101 moles, right? And we're going to see that there, for every 1 mole of barium chloride, there is 1 mole of barium sulfate. How do I know that? Where do I get 1 to 1? Go back to that balanced equation. This is a mole ratio. It's been a while, but you've done this. Mole ratios are given from the balanced chemical equation. So those are from coefficients. See, we have 2 NaCl's here. No other numbers are present. So that indicates it's an understood 1, an understood 1, and an understood 1. That means every 1 mole of barium chloride will produce 1 mole of barium sulfate. So it's a 1-to-1 ratio. That's where we're getting this from. So moles of barium sulfate times 1 mole barium chloride over 1 mole of barium sulfate times 1. And then divided by 1 obviously doesn't change the answer, but that is how we convert from moles of one thing to moles of another in the same chemical equation. So that tells me that that's 0.0101 moles of barium chloride. Now I can take those barium chloride moles and change them to grams. Why do I want to change it to grams? Well, reference back to our instructions in part B, and it says find the percent of barium chloride by mass. Mass means grams. That means I'm searching for grams. So now I take the 0.0101 moles of barium chloride and I'm going to multiply it by the molar mass of barium chloride. And I find that information from the periodic table, the 208.23. I've shown how to calculate that here to the side. Simply getting the mass of each thing, adding them together to get the total. So once I do that, I've now converted moles of barium chloride to grams of barium chloride. Okay, almost there. Last step, I need to find a percent by mass. Okay, so I'm going to take the grams of barium chloride over the grams of the total mixture. Why? Because percentages are always a part of the whole. So I'm going to put that number in here and divide it by the 6.75 grams of mixture. Where did this come from? Where did you get this? That was given. To look way back, but that number was given to us way back in our problem. And number 3, I want to show you the student dissolves a 6.75 gram sample of this mixture. So that's how much of the mixture we have. All right, moving on to problem 4 and our final problem of this section. You've got a mixture of calcium carbonate this time and sodium carbonate, and it's found to contain 35% sodium by mass. And we're told to calculate the percent of sodium carbonate by mass in the mixture. This is similar to what we did, but it's almost backwards, right? Instead of finding the one tiny piece, where we have that information for the one part, the one element, we want to find the percentage of the whole compound. So we're almost working backwards from some of the other problems we've looked at. We're told to assume the total mass mixture is 100 grams, and the mass of the sodium is 35 grams. So we've got a couple of numbers to work with. So the first thing I want to do is change sodium to sodium carbonate. Because I want to find percent by mass, so I've got to find the grams first so that I can take that, work that into a percentage problem and part over the whole. So first I'm going to take my 35 grams of sodium. I'm going to set that up in a ratio here with 45.98 grams of sodium. Where did that number come from? Well, if you check your periodic table, sodium has a mass of 22.99. But I want you to remember there are 2 sodiums in Na2CO3. So I've got to multiply that by 2 to account for how much mass the sodium takes up. Now the total of sodium carbonate's molar mass from the periodic table is 105.99. I've shown you how to solve that here to the left. So in your calculator, 35 times 105.99, enter, divided by 45.98, you're going to get 80.68 grams of sodium carbonate. Almost done. Step 2. Now let's turn that into a percentage because our problem said find the percent by mass. So we're going to take that number, 80.68 grams, and we're going to divide it by the total mixture of 100 grams. Where did I get that 100 grams? Well, it told us in the problem, right? Given of 100 grams, we put that in here on the bottom. So 80.68 divided by 100. Then we're going to multiply that number by 100. We're going to get 80.68% as the percent by mass of sodium carbonate. That concludes section 1.4.